So hey everyone, welcome back. This is the second video of the graph series. So the problem we'll be solving today is graph without long directed paths. So this problem came in Codeforce around 550 div 3 and it is a 1700 rated problem. So I picked this problem because it has a certain concept in it that I wanted to explain. So let's just start. So we are given an undirected connected graph. It has n vertices and m edges. There are no self loops and multiple edges like any common graph. Then you have to direct its edge in such a way. Basically, you have to make a connected undirected graph to a connected directed graph in such a way that the obtained directed graph does not contain any paths of length 2 or greater. And yeah, so where the length of the path, which is pretty obvious. So this is the simple question we have, and we simply have to print yes if it is possible, like if we can convert the undirected edges into that form, which basically means if you can make the connected undirected graph to a connected directed graph and you don't have any paths of length 2 or greater, you have to print yes. And then you have to print a binary string like this, which basically means if it is 0, then yeah, so if this is the edge 1 to 5 and you have marked 1, that means the edge is from 5 to 1, and if you marked it 0, basically it's 1 to 5. So that's the logic of this question. So yeah, so basically you just have to print if it is possible, and then if it is possible you have to like show like what will be the direction of the edges. So that's the whole question. So now let's directly move to the solution. So yeah, now looking at the solution, let's first make some obvious assumptions. So let's consider this graph. Can we like, is the answer yes or no for this particular graph? Like, as you can see, this is a connected undirected graph. So let's just see if it is possible to convert this graph into a directed graph which has no two which does not have a path greater than or equal to 2. So let's just say I made this arrow. I cannot make this arrow as this one, like I cannot direct it this way, so I have to make it this way. And then this arrow, if you'll see, if I make it this way, then I'll have this path, and this path is of length greater than this path is of length 2. The other option I have is again the same thing, this and this. Then now here I have a path of greater than a path of length 2. So it is not possible up here. This case is not possible. So now I think you got the gist. Like when we are getting no, like you can try many other combinations of directions, but you'll see that you won't be getting an answer to this. uh, like this connected graph cannot be connected to direct graph with a path path less than 2. So now let's consider a case where it is possible. So let's just say we took this. So um, something like this. So you made this, then you have to make this as this, then this will be this. So you can see like you can't see a path like path of length 2, or obviously you can't see a path of equal to. So so you will print a yes for this. So now if you'll see one obvious assumption we made, consider a node. Okay, this is a node n1. If this node has a edge directed towards it, then this node cannot have a edge going out from it like this way. This is not possible. This is not possible for any node, because then there is a path of length 2. Then there will a path of length 2 which is not allowed. So this is the first observation. This is the first observation. What is the first observation? For any node, either it will have like all the edges will be pointing towards it, or all the edges will be pointing away from it. You will never have a node like it has this, and then it has this also, because there are two in degree and one out degree. That's not possible. Either in degree has to be 0, and out degree has to be greater than 0, or in degree should be greater than 0, and out degree should be equal to 0. Like, these are two very basic common assumptions that we are making, and this is obviously true for this. Like, this is not an assumption, this is a fact for this problem, that either all the edges would be pointing towards it, or all the edges would be pointing away from it. It is like this case is not possible. So let's just mark it this way. Okay, I'll clear this slide, 1 second. So let's just see it this way. This is a node. Like I'm taking a graph in which it is possible. So let's just say, so we'll make a current, like a correct directed graph. So this is a correct directed graph, and you'll be printing yes for this. So let's just color our nodes this way. Whichever node has a in degree, like it has nodes coming towards it, like only nodes coming towards it, it should be blue in color. This node has, and this node, like these two nodes are the nodes which have edges coming towards it, and the other one we have is these nodes which have edges going away from it. So this is red and this is red. So this problem completely became a bipartite problem. How it became a bipartite, like if you want, like I'll put on some videos that you can refer for learning what a bipartite, but it's a simple concept. um, Bipartite graphs are basically something like this. How should I explain this? Like you can see videos which explain it much better, but basically there should be distinct coloring. I don't know the exact definition, but I just know the definition of what is a bipartite graph. So if I make a bipartite graph, so I will try to color my bipartite graph this way. Like if this is red, then these two cannot be red. These two have to be blue. Okay, these two have to be blue in color. So these two would be blue. This is blue. This is blue. Like you cannot have two same colors connected with the same edge basically. Then this is blue. Then this is blue. Then this blue cannot have blues over here. So here we'll be having red. So a red up here, a red up here. Here we'll be having a red. Here we'll be having a red. Then here we'll be having two blues. Here we'll be having two blues. And then finally here we'll be having a red. Here we'll be having a red. So this is how a bipartite graph looks like. And if you see, this completely aligns with what observation we have made. It completely aligns with what observation we have made, because as we said, blue color are the nodes in which degrees are coming, like in which the, sorry, no, not degrees, in which the edges are coming towards the blue one. And from where they'll be coming? They'll be coming from the red ones. They'll be coming from the red ones. So the pattern is always like this. From red, it will go to a blue one. From red, it will go to a blue one. And similarly, from this red, it will go to other blue one. You're getting the idea, right? And so this is basically the idea. So if your graph, you are saying satisfy these, like it satisfies the condition, then it should satisfy the condition of a bipartite graph. Like it should satisfy the condition of a bipartite graph. And you can please read about this bipartite graph. It is a very famous concept in, like, that is the reason I picked this problem, because it has this bipartite concept involved. So your graph should be bipartite in nature. And if it is so basically there's also a fact that every graph, like every tree is bipartite. Every tree is bipartite in nature. Every graph is also bipartite, but it isn't bipartite if it has a odd length cycle. For example, I showed you the first example. This is an odd length cycle, and this can never be bipartite. But you can see why this thing was bipartite, because it had an even length cycle. So if your graph has an odd length cycle, it is not bipartite. If it has an even length cycle, it is bipartite. If it has no cycle, then also it is bipartite. So this I just gave you a brief how to check if it is bipartite, but there is a completely different BFS technique that we'll be using to color the nodes. So basically, if you have the nodes colored, so let's just say we are naming all the blue ones as okay, let's just say we are naming all the blue ones as 1, red ones as 0. So when you'll be traversing this edge, you can just say that if like then it is very easy to name, right? You can just say if so for example, this was node 5 and this was node 6. So you will say that see out for this particular edge, for the edge 5 comma 6, the answer is color of 5, let's just say less than color of 6. What we'll be getting is 5 to 6 equals to, what is color of 5? 1. Is 1 less than 0? No, it isn't. So you'll be getting a 0. So you got it right. Like this is how we'll be so 5 to 6 we have made it 0. Then let's just say this was 5 to 4, and in input we were given 4 to 5, 4 to 5. So we'll just simply check color of 4 is less than color of 5. Is it true? Is it true? Yeah, it is true. So 1. So that basically means an edge is coming from 4 to 5. And if 5 to 6 is 0, that means an edge is coming from 6 to 5, not 5 to 6. And if you'll notice one thing, all bipartites are complementary. As you can see, this is the exact same graph like this one, but just the colors are different. Now red is blue, blue is red. So in your answer, if your answer is suppose 1 0 1 1 0 1, then 0 1 0 0 1 0 1 is also possible. Like complementary of that binary sequence is also a correct answer. It just depends. Like if you're saying 5 to 6 is 0 or 1, like it's up to you. Like it doesn't matter anyways. So but I think it is given in the question that if 5 to 6 is like, if edge is from 5 to 6, then print 0 or 1. So you just like, you got the idea. Like printing is basically very easy. So the main idea was to check if it's bipartite, and then if you know the coloring, then you can just easily assume, like if blue, yes, if 5 is blue, 4 is red, then edge is coming from red to blue. Like that you can make your own, like that you can make your own convention. So let's take a look at the code now. So this is the code, exact code. So um yeah, so this I wrote a simple bipartite thing. You can also, like there are many methods to write the bipartite code. You can write it via BFS, you can also write it using DFS, and in the end just print if the color is less. Like please try to figure this out. It is simple. Like you just have to check the coloring, like what color was made, and how to run that. Like I'll show you the DFS thing, how I'm running the DFS thing. So initially I have made color as -1. It means that it is not yet colored. If it is not yet colored, I made a global pause, I think. Yeah, I made a global pause. That basically means if it is possible to make the graph as bipartite. You can find like similar bipartite codes in YouTube, unlike other videos also. Please refer that. And then what am I like what I'm doing is the current node, the parent node, and what color I am assigning to the current node. So currently I'm assigning 0 to the current node. So the color of the current node is C. If parent is not equal to -1, then if the color of my parent is 0 and my current color is 1, so I basically used a map technique, but it is not even necessary to use a map technique. Like I was trying to implement something else, so you can skip this part. It will just make it it will just complicate the code. So skip this part. I'm just traversing over all my adjacents, and if my adjacent is not colored, then I'll be running a DFS for that node, but with an opposite color. 1 minus C, as you know, if my current color is 0, then my adjacent color would be 1. If my current color is 1, then 1 minus 1 is 0. My adjacent color would be 0. So I'm running a DFS for that. And if my adjacent is not my parent and it has the same color as mine, that means it is already colored, right? If it is already colored and it has the same color as mine, then that's the fact for bipartite. It is not allowed. You saw in the visual representation, right? Like two nodes with the same color and connected to each other are not allowed. So if my adjacent is not my parent and it has the same color as like whatever I have colored myself, it is already colored, then it's not possible. So simply pause false, and you can just check here. If it is not possible, see out no. Otherwise just iterate over all the nodes, and like I have stored the edges also, so just check if their color is less than the color of the other one. So this is basically the idea. And as I said, complementary answer is also possible. If the answer is 1 0 1 1 0, 0 1 0 0 1 is also possible. So I just wanted to show you an implementation of bipartite, like where bipartite, like it's a good concept, and this question was a good application of bipartite. So Yeah, I hope you learned something. Yeah, thank you.